All right, so let's talk about work and energy, the work energy theorem. And this simply states that whenever work's done, energy changes. So energy is one of those things, it just kind of changes from one form to the other. We always keep it, it's always there somewhere, but it could change from different types of energies that we talk about. So if we want to increase kinetic energy, we've got to do some work. We've got to do something. Maybe we burn more fuel in the car to get it up there. So if the object's already moving, we've got to apply some work to get it to stop, for instance. That's a change in kinetic energy. Whatever our change in kinetic energy is equal to the work done. And therefore, what we're talking about here, this work energy theorem, is simply a relationship between work and energy. Those two things are related. If I do work on something, I either am applying energy into it or, getting energy out of it. All right, so here's our example. We have work, and we simply say that work is equal to the change in kinetic energy. Work equals change in kinetic energy. So therefore, the net work that I put in is based on the net force that I have. If I've got no change in kinetic energy, I haven't done any work. No matter how hard you push against the wall, if the wall doesn't move, you have done no work at all. Absolutely nothing. You're lifting weights and you're trying to max out, and you're trying to lift that object off your chest, and you might be straining and sweating and everything else, and your body is draining, and you might be exerting a lot of force, but you are doing no work whatsoever if you do not lift that weight. Okay? So if you push on a box, it doesn't slide, no work. If you're on a slippery floor, maybe when there's no friction, and it says the work of your push times the distance appears as kinetic energy. So if there's no work or no friction, I'm going to get some work out of it. If there's friction, friction is resisting your force, and we're not getting any work out of it. So what we're talking about then is the net force. So we've got a force that we apply, friction, he decides to apply a force the other way. If my force that I apply is bigger, the object moves. If I apply a little force and friction can apply the same force the other way, the object doesn't move. And I therefore do no work whatsoever. In order to work, I have to change the energy, the kinetic energy. In order for kinetic energy to change, there has to be movement or change in movement. Okay, it also works if we're slowing something down. The more kinetic energy something has, the more work I have to require to stop it. It takes twice as much energy to stop it. That would mean I need twice as much work. Take a look at this. Here's a bike tire. The guy slams on the brakes. Notice how right here, this is an infrared picture. Notice how that got warmer. So where the tire skidded across the road there, it got warmer. And they'll show you a picture here of the bike tire itself. It got warmer. Okay, so there was some energy transferred in order to get the bicycle to stop. Or if we apply a car, if we apply brakes in a car and we're trying to slow it down, the faster I'm going, the longer it takes me to stop. Take a look at this. If I'm going 45 kilometers per hour and I slam on the brakes, I come to a stop in 10 meters. However, if I double my speed, if I'm going 90, that doesn't take me twice as far to stop. It takes me 4 times as far to stop. Or if I'm going 180, this is now 4 times what that is. So therefore, 4 squared, it's 16 times longer from here to here than it was from here to here. Okay? So this is why, we always tell you not to drive too fast. The reason is because it doesn't just, if you're driving twice fast, it doesn't just take twice as far to stop. It takes 4 times as far to stop. It's also why, when you're driving, the faster you drive, the farther you should be apart. Cars should be apart. So if you're on the interstate going 70, you should be farther apart than if you're running through town going 25, because it takes much longer to stop. Okay, kinetic energy can also be in a lot of different things that we don't think of, like heat, sound, light, and electricity. Those are all examples of kinetic energy. So when we talk about heat, heat is random molecular motions, particles bouncing into each other. We sense that as heat. That's what we pick. That's how our senses perceive that particular thing, as in the form of heat. If you have sound, that is molecules that vibrate in very rhythmic patterns. You know, things that our ear is attuned to picking up and we can hear. And then light is simply the motion of electrons. And, you know, actual light that we can see has to occur in a certain frequency in order for us to be able to do that. And then the last thing they talk about is if we have moving electrons, that's what we call electricity or electric current. All right, so a friend says that if you do 100 joules of work on a moving cart, the cart will gain 100 joules of kinetic energy. Another friend says this depends on whether or not there's friction. What do you think? Well, I think the other friend was pretty smart. And it does depend on whether, you know, you could gain 100 joules of work. You could do 100 joules of work. Doesn't necessarily mean you're going to get 100 joules of kinetic energy, because chances are you're going to lose it somewhere. Doesn't necessarily even have to be friction. It could be some other things. But, you know, we're always talking about net force. We're doing it. When the brakes of a car are locked, the car skids or stop. How much farther will the car skid if it's moving 3 times as fast? Remember, we're squared. So if it's 3 times as fast, we're moving 9. I think this is kind of a confusing thing. But here they're saying, you know, originally we had V, now we have 3V. So we end up with 9 times as fast, or 9 times as far, 9 times as much kinetic energy in this example. All right, conservation of energy. You know, here's the thing. Energy cannot be created or destroyed, but it can be changed. It can change from one form to another, and we can do that over and over again. Okay, so more important than knowing what exactly energy is we need to understand how it transforms, because that is what we use. That's the important thing. And so we're going to talk about that process. So here's somebody firing a bow. We've got this potential energy. As she pulls back the bow, she lets go, and it becomes kinetic energy. And that energy transfer can do a lot of work. Okay, so you've got potential energy when it's pulled back, turns into kinetic energy. That energy is then delivered to the target, and obviously, you can kill something with an arrow by delivering that much force to the object. Okay, so the small distance the arrow moves, multiplied by the average force of the impact, doesn't quite match the kinetic energy of the target. However, that's because we're going to have the target and the arrow going to be a little bit warmer. So we've lost some energy to heat. If you hear it, if you actually hear the sound when the arrow's flying, it's going to lose energy to that too. We're going to hear, that's going to be another change of energy that we have. All of those things are just changing back and forth. But if you found all of the total energy that that was there, or every different thing that's formed into, it would be what it started with. All right, so the law of conservation of energy simply says that the total energy is going to stay the same, might change from one form to another. We could be talking about all kinds of things that's as simple as a swinging pendulum or as complex as an exploding galaxy, but it's all the same amount. The energy that we have in the universe is there, and it's going to be the same amount tomorrow, same amount 100 years from now, so on. So here's an example of a car, one of those little spring cars. You wind up the spring, it now has potential energy, and we change it into kinetic energy. Typically, you don't get all of it out, so you got 10 joules of potential energy. Maybe you only get 8 joules of kinetic energy out of it, because you lose 2 joules in the form of heat. And very likely, any friction between the floor is going to create that heat, and so on. So you're going to lose some of that to friction, which is really heat. Or here's this woman, big fire in her apartment, jumps out, hopes the firemen will catch her. At the very top, she has 10,000 joules of potential energy, and she's not moving, so she'd have no kinetic energy. As she's a quarter of the way down, there's been a conversion So now some of that potential energy has been changed to kinetic. So she's got 7,500 potential, 2,500 kinetic, but it's still 10,000 like it was when it started. Halfway down, 5,000 of each. 3/4 of the way down, not as much potential energy anymore. Lots of more kinetic. She's going a lot faster now. And at the very bottom, you know, it's all been changed into kinetic energy. This is right before she hits. It would be all kinetic energy and no more potential energy in that case. And we can think of atoms too when we're talking about it. So atoms are matter. We have these of concentrated energy. And, you know, these atoms want to arrange themselves in a certain way. And if we rearrange those things, it either takes energy or we get energy, you know, out of it. And, for example, the sun rearranges hydrogen. It takes hydrogen, fuses it into two different hydrogens together, fuses it into helium, and that nuclear energy gives off a lot of heat, and that's where all the energy from the sun comes from. So we have that nuclear fusion. So we then collect all that energy on the earth, or not all of it, but a lot of it reaches the earth. Plants take it. Plants turn into, you know, die over millions of years. They become coal. And guess what? We now use the coal. So this was energy that came from the sun. The sun got it from hydrogen, and so on. And so this process continues. It just continually transforms. You know, sometimes we get, you know, the sun gives us life, you know, gives us plants that grow, and we eat plants. Animals eat those plants. You know, maybe later they're changed into oil, or maybe we just use them. You know, we grow plants. Animals eat the plants. We eat the animals, and we get the energy eventually that came from the sun. So there's all these things that they talk about. Here's another example. The sun evaporates water. Water turns to rain. Rain gets trapped behind a dam. We then take the energy there and change it into electricity and so on. So it's all these conversions that take place all the time that are going into this. I think it kind of keeps going on this, but I think you get the idea.